is a parking lot. Anything going on?
Yeah, I had a question.
Okay.
Like, I don't even really know where to begin with this.
Determine the greatest load P. Focus, come on. The load P that can be applied to the truss so that none of the members are subject to a force exceeding 2 kilograms of tension and 1.5 kilograms of compression. So this is kind of like, what's the maximum
Right. Like weight
you can put on that chain system. It's very similar. It's the same idea, right?
So I guess if you
could solve it with P as a variable and come up with, algebraic expressions for all the forces in terms of P.
Okay.
Or you could just set P equal to like 100 newtons. Or
And
P
guess.
equals to like, not 100 newtons, that's way obviously too much, but you could set it equal to 1 kilonewton and figure out what the forces are. And it's a linear system, so you can scale it according to whichever one, gets violated first.
So,
right. So if you set P equal to 1 kilonewton and you solve for these, and these guys are in like, I don't know, maybe these are in like 1.5 or 1.7 kilonewtons of compression, and this one's in like, 1 kilonewton of tension, then, how much can you scale this whole thing by? If you make it 2 kilonewtons, then that would exceed, probably it would be 3.4 or something, right? But if you, which one, as you scale up P, one of these is going to exceed the limits before the other, and then that's the maximum P you can get.
Okay.
Make sense?
Yeah.
So that's a more empirical way of doing it, but if you want to just do it algebraically, that's fine too.
And you'd get an answer in terms of P?
Yeah, your answer would be in terms of P, and then you just set P equal to, set the force equal to 2 and solve for P in each equation, and whichever P is smaller is the maximum P you can have.
Right. Okay.
So just like the other ones.
Yeah, just like those chain ones.
Gotcha.
How about you guys? Having fun on the phones? Anything I can help you with?
Should we make 2 cuts here or just the one and like focus on this side?
Well, yeah, so this is the one like from the in-class exercises, right? You have the answer to that one. So when you do this one, you have a choice because this one's floating in space. And you can, if you solve for the reactions, you can do the left section, or you can just cut it there and just solve for the section that's floating in space. And that will be easy to solve. It's easier to solve that side than to do the reactions first. It's less work.
So
right you can do it either way. You'll get the same answer. The right side's a little bit easier.
I didn't get a chance to see this when it was in class.
It's on the video.
Oh, okay.
Yep.
Do it ourselves.
The calculation about those.
In order to identify a zero force member, should we start doing calculations?
Oh, I see.
Well, remember the slides? Because we looked at that in lecture, right? You were there. So those slides are available, and the slides are saying there's a key. Well, one way to find zero force members is to look for 2 collinear members that don't have a load, but the only 2 collinear members you have are ED and DC, and they have a load there. So there's probably no zero force member there. Yeah, that could be a zero force member.
Also there's EB. Oh, not EB, maybe.
Yeah, so think about, one thing you could do is just draw the free body diagrams at each pin, and then you might be able to figure out which one of those are going to be zero force.
So there's no way to eyeball it.
Well, the common way of looking, the easy way for, when you have 2 collinear ones that don't have a load is one way. So like if D didn't have a load applied to it, it would be DB would be a zero force member, but it does, so it's not a zero force member. There are other zero force members there. And yeah, you'll just have to kind of
just do the calculation about each.
You could try that. You do the calculation about each one, and you'll see which ones are zero. I mean,
that's the safest way. Guarantee that
Until you really get understanding of it, yeah. I mean, you can look in the book and see if there's any more, you know, advice for zero force. Anyone have a book? Anyone have a book handy? Anyone have a textbook handy? Okay.
I have one, but it's in my car.
Yeah. Yeah. I might have one. Let me see if I have one on my. Let's see, where would that be?
Because if you multiply this one by 2 and this one by 2, so you scale it up, you get 4, 3.
I think I have
So you
a
get 3
version
here,
of Fiddler online. Let's
4
see.
here, 3, 4, 5. Yeah.
Yeah, here it is.
Well, in this case, it is. If they give you 15, 20, and you also know. So you have to multiply or divide by.
This is why having a book, you know, engineers, you got to start having a book with you. And I don't know if you probably use it when you do the homework, because it's easier to find stuff in a paper copy of the book, and it's not that expensive.
It was actually $28.
That's nothing.
From Amazon.
Yeah.
I was talking to Devin the other day, and he was saying like now he's start taking mechanics of material, fluid mechanics, dynamics over a San Jose State.
Mm-hmm.
I don't know if you know which Devin I'm talking about.
Devin McKee?
Yeah, Devin McKee.
Uh-huh.
And he said that now I needed a book, but I already saved the PDF that he posted at that time that he was taking it. But he said like I still need a book right now. So you did the best thing that you buy the book. He
Yeah.
was telling me.
He bought the statics book finally?
Yeah, no, he didn't buy the static book. He just have a PDF on his
But
computer.
now he bought it so that he had a paper copy? Is that
No,
what
he
he
was
said?
telling me that you did a good job that you bought the book already because I'm having a hard time right now with there.
So he wished he had bought the book.
Yeah.
You just pay the $15. It's really nothing.
Yeah, but he's like it's all about statics.
It's all about statics, you guys. Did you guys buy a book yet?
Yeah.
Okay, good. That's what he's saying. A mechanical engineer, it's all about statics. He was talking to Devin at San Jose State, who just got an E copy last year, and he's like, I wish I'd gotten, because otherwise like I already got my hard copy. Like I wish I'd gotten one too, because it's all statics. That's what you do over and over again as mechanical engineers. And it's just so much easier to find stuff in a paper book. Here it is.
Yeah, to let me book. It's harder.
So these are Air Force number problems.
So the next is chapter 5, 6, and 7, or just 5 and 6?
I think just 5 and 6. So,
Because this, you can get ED.
so they're showing you some examples here. Looking at pin D, FDE, FDC. If you, you see what some of the reasoning they're doing here is, and I can't show this, I don't think, to the video people. Let's see if I can show this to the people. If I share my screen, maybe I can do that. Without killing the recording. I'll be surprised if it doesn't kill the recording. It's still on. It's still recording. So, when you have something like this here, how do you analyze that? Well, if you draw the free body diagram and you tilt the axes, you have the X and the Y axis here, then this is why I hate electronic books. You should get a freaking paper book and bring it to class so I don't have to do this. So anyway, when you see it this way, right, the only force that can provide, when you tilt the axis, the only force that can provide a component along the y direction is FDC. And if it does provide a component along the y direction, there's nothing that FDE can do about it because it's perpendicular to the y axis.
That's a zero force member.
Yeah. Because if there was a force in FDC, it would give you a Y component that could not be dealt with by FDE.
So
See what they're saying? The sum of the FYs equals 0. The only FY component is FDC sine of theta, right? FDC sine of theta is the Y component of that FDC force, right?
Mm-hmm.
And that has to equal 0 because that's the only force in the Y direction. So it must be 0.
So again, this one in you see DCB. No, we have a load over there. It's different.
Well, if you draw the diagram at C, it's very similar.
Mm-hmm. But we have a load over there.
So there's a load right here. But they're doing the diagram at D with no load on it, right? And do you see a load there?
Mm.
Yeah, so you do a diagram at C, it's the same, very similar to the situation here when you have a diagram at D, there's no load there.
So yeah, you can like the CB is a zero force member also.
So then he's doing the sum of the Fx is equal 0. That's FDE plus 0 because that force has to be 0. So therefore FDE is 0.
Huh. Yeah, okay.
Looking at this truss at D, figure 612A. These are pretty easy because you got these collinear members, right? So AD is 0, AC is 0.
But aren't there vertical and horizontal components of the pin?
We weren't talking about E, we were talking about point C. Point C.
Oh, yeah. So DC is zero force?
I feel DC is 0, but BC cannot be 0 because we have a load over there. It has to support it.
Well,
Or maybe.
BC cannot be 0? Why? So again, did you see how they said you got to write? Yeah. So basically, draw the free body diagram for each one of these things, and you'll see, right? So here's another one. Which one are they doing here? What is this? FCG. Trust here. Yeah, they were doing it here. You know, when you draw the free body diagram, you're going to look for components where there's like only. If you tilt the axis here, right, the only force that is going to be oriented along the x-axis is FDA. So if you do the sum of the fx is equal 0, you only have one term in it, FDA. Therefore, it has to be 0. I want you to try doing that. I'm not going to tell you the answer, but I want you to start drawing the free body diagrams and making these reasons. Right? You're going to look for when you can tilt the axis certain ways. There's only like one force that can give you a component along that direction. Then it must be 0.
I'll see right now.
Yeah.
I had a kind of like a weird question about zero force members.
Okay.
This question isn't asking for it, but like me and David were just like talking about it, kind of just trying to see.
What was your question?
So we were looking at an example on the slides, and it was kind of a similar thing where the force was located at the top. So like the force was up here, like at E essentially.
Yeah.
And that the beam from like the vertical beam below the force was like a zero force member. But in this case, having the force at the bottom, does that change that?
Well, you have to take everything on a case-by-case basis, and there is no, I mean, various things can change the situation so that...
that's not the only thing to worry about.
Yeah, so this one doesn't have any, this truss doesn't have any zero force members in it. You have to do the analysis of method of sections to find these forces. This is not a zero force member problem.
But like, so there's no zero force numbers.
No, there's no zero force number in this truck. So you're kind of wasting time. You should just do the method of sections and just solve for the force.
Well, we were just like trying to understand the problem.
Well,
That makes sense that I think about it. It's like
did you watch the lecture on method of sections?
No, I didn't.
Okay, well, that's the problem. so,
Well,
so you got to watch that before class. Isaac, how else are you going to get this so you can do it in class? Otherwise, it's not explained. Did you watch the lecture on method of sections? Okay, then you have to teach it.
I haven't fully internalized it yet.
Well, the general approach is that you cut the structure and you let's see if I can capture this thing. So if you're not going to watch the lecture, this really defeats the value of these sessions. You know, that's the problem. And it's not a very long lecture, so you guys should try to figure out a way of doing it. Or is this thing? Why am I not getting this? Oh, it's right there. Can I slip this thing?
Yeah, I don't think you can assume that.
Okay. I think this will hide this thing. All right.
Okay, you said great. Okay.
So when you do the method of sections,
Yeah, true.
what you do is you know, in general, you could find the reactions, right? So you're going to have a GX and GY, and that's oh wait, one of these is a roller. Or what is that?
I think they're the same.
Actually, they're both pins. However, this guy just has one member vertically erased. So there's only really going to be a GY here, because you can kind of convince yourself that there's no need for a GX, because what is going to be pushing in the X direction? This is like a tension force. So it can't actually push down, if that makes any sense.
Okay.
There's only a GY, or a GX, AX, and an AY. And in general, you can do that. And in general, it doesn't matter which side you solve. But if you're going to do the left section, you're going to have to solve for the reactions. If you do the right section, you don't have to solve for the reactions. For the right section, you cut it and you look at this right section, and you redraw that as a rigid body. This is like a chapter 5 problem. So in other words, you draw it with all the forces acting on it, and their direction and their angles, right? And so you solve for those forces. But each one of these members now is cut. So there's a cut here. And you know, you got this force here, you got this force here. These are the forces which are again assumed to be in tension that you have to solve for.
So even though we cut it, we still have to like write those down and then cut through all of them.
The forces that they're asking you to find are FFE, FFC, and FBC, right? And the only way to find them with the method of sections, and the nice thing about the method of sections is it's faster. It's faster because without the method of joints, you're going to have to solve for all the pins, you know, to get to that point, and you solve those forces. It's a lot of extra work. The method of sections goes straight to the point. Just find these 3 forces. And because you can cut this body and the forces are exposed there, when you cut those members, those forces are actually acting kind of internal to those members, but they're working through them and keeping that force on it, right?
They're not stuck to these points here.
Yeah. In other words, if you look at what's happening in a rope everywhere along its line when it's in tension, right? If you cut it anywhere, if you do an imaginary cut, the only reason why that rope is not splitting apart is because there's actually those same forces are acting at the cut at each point in that rope to keep that thing from splitting apart, right? Those are atomic molecular forces, right? And And so you can expose those forces by cutting a member. We're going to look at internal forces in chapter 7 in more detail, but this is sort of our first exposure to them. And so those forces, to stretch, these forces again are all in tension because they're stretching those beams. And you can take advantage of the fact that they're converging at different points. These 2 points are concurrent points. Two forces, FFE and FFC, are concurrent because they're both pointing to point F. Forces FFC and FFB are concurrent because they're both leaving point C. So you can, because this is a rigid body now. This is like chapter 5, which means it's not just a single point. You've got stuff at different, attached to different points on this 2-dimensional body. You actually have 3 equations that you can use to solve for 3 unknowns: the sum of the fx's, sum of the fy's, and the sum of the moments. Oops, let me get that thing out of there. I think that was in the other thing. Those all have to equal 0. Now you can pick different points to do the moments, and the beauty is if you pick point F, like so to solve this one, if you did the sum of the moments about point F, okay, which forces are going to give you a moment about F? Well, the 2 load forces, right?
Yeah.
And FFB, those are only 3 forces give you a moment about F. Okay. If you decide to do the sum of the moments about C, which forces are going to give you a moment about C?
The external force.
FFE and the 800-pound force. It's trivial. It's a lot easier than doing anything else, right? So, and then the third force you can only get by doing like a sum of FX or sum of FY. When you get the other 2, it's pretty easy to find. That's basically it. So it doesn't matter which side you look at. You can do the left side, but here you're going to have to find the reactions because they will affect the forces there.
Yeah. What principle makes it possible to just be able to cut it wherever you want?
What principle makes it possible to cut it wherever you want?
Yeah. You find the forces that way.
Because
it seems like it would like be wrong. Against something.
Well, it's an acknowledgement of the material properties of that structure. When you design a bridge, like if you do that balsa wood bridge thing for the final project, right? Those balsa wood members are like fibers. When you stretch them, they resist, stretching or breaking. Why is that? Intermolecular, interatomic forces, right? Those bonds, atomic bonds, and that's what we learned about in engineering 4, the materials course, which we're offering in the spring, in case you guys have the capacity to take it. But so you can stretch those things, and they won't. Those forces are like the same kind of forces that are acting externally to this thing. You can actually articulate those internal forces. The reason why we can get away with that is because that's what's really happening. We're not getting away with anything. We're just reflecting what's the reality. Anywhere you decide to cut that thing, if you look at any, atomic bond here, you'd be cutting it, right? That atomic bond is cementing those 2 sides together with forces, with atomic forces. Electrons and protons, bonding, whatever. Those are pretty strong forces. That's what's doing, because you got a lot of them. All right. Okay? Yes. Good luck.
Yeah, you need this one. Or you don't want to do this? No, you want to do this one. Yeah. Yeah, without to, because we already know where.
More questions?
I think so.
Yeah.
Well, okay.
Yeah, so
So like I did that about point C,
let's just say found
Mhm.
AE.
and I got like 2 zero force number over there.
Yeah.
That's right, right?
Mm-hmm.
So then you could plug one of
Yeah.
these into this one.
Yep.
Cool.
And where else did you suspect might
did
be
you
a
got-
zero force number?
I did.
I'm
I got
definitely sure
E
there is
between
one
5.
here.
Okay, so then you could prove that to yourself the same way.
Yeah. But when you ask this compression, do you want us to do the calculation to show you?
Well, how are you going to convince
Yeah,
somebody, right?
Yeah. Yeah, that makes sense.
Yeah. It's either going to be right or wrong, but you got to figure out which one it is. Okay. Make sense?
Yeah. Which makes sense.
Okay. You heard me? You were listening? You didn't watch the lecture either, did you? Okay, good. So another option, we really want to go into this flipping thing, is I could have quizzes that you have to take the night before you do the problem. So, right, I want to watch the lecture, take a quiz right away, and then that would be, it's too much. You'd actually have to work in the class. A multiple choice quiz, it could just be those reading quizzes, and I could just throw those up there right after you watch the video. Yeah. Motivating people with fear. It's the best way. That's why schools are so prevalent. Fear of getting bad grades.
Well, I didn't. So I figured out what the angle was. Yeah. But if you put in the tan inverse.
Questions?
Where's the fifth one? You said you found the 5.
I only got 4.
Are you going to 4?
Yeah.
Okay.
4 zero force numbers?
Yeah.
I don't know if it's that possible.
Which ones are they?
Can't
Which ones?
So FAE.
FAE, FCB, CD, and
DE.
and what?
In what?
DE.
And DE. Yeah.
DE is the zero force number.
Tom, we had a question.
Yeah, go ahead.
So, can we assume that this will always be a zero force member because it's between a roller and a pin?
Can you assume a zero force number between a roller and a pin? No. If there was a load hanging down at A.
Well, yeah. I mean, like if you don't have load hanging, or if any force in that line, like in that axis,
Yeah.
you can say it's 0 force number, right?
It's the same reasoning that you did for all of them, right? If there's only one force in a particular dimension, then yeah, it kind of has to be 0. But that's the fundamental thing you got to keep looking at. So why is so I guess what you're saying is if that's a 0 force member there,
That one's a 0 force number too.
then your free body diagram has 0 here, and there's nothing else that could, yeah, so if that has to be 0 as well, yeah, DE looks like it has to be 0 as well.
Is it
Very
possible
interesting.
to build something that has
Well, you know, it will have some force on it, but I think, but compared to the actual 3 kilonewton force, it's going to be really small, right?
Yeah.
It's more of a stabilizing force to keep it from buckling. So that's 0. So then, yeah. So then you basically have this has a load, and so really it's just what DB, EB, and BA that has a load in it, right?
Yeah, I
That
guess.
is a compressive load. That is a tension load. That is a compressive load. Yeah, pretty interesting, right? But if you took the zero force members away, then this wouldn't be supporting, right?
Right.
So there has to be some force there to keep it from
Yeah.
collapsing, right? But it's not very big.
Crazy.
Yeah. Mm-hmm.
Weird.
Yep. Good questions. Okay, how's the Joker doing?
I'm the Joker.
I think so.
Joker.
Joker's wild.
Pretty good session.
Any
Okay,
questions?
Actually, I did have a question.
Mm-hmm.
So when we break it down into the fx, fy, and moment, in this case, I did moment on f.
Yeah, I would actually recommend. Remember how I told you? I recommend doing 2 moments.
Okay.
You do a moment about
At
F
A?
because that's how you can find this force.
Yeah. And
Do a
then
moment about C
C,
because that's
okay,
how
I
you
was
can find
thinking
that force.
But my question was, do we take into account the tension here? Is that part of the summation?
No,
No.
because look at your diagram.
Okay, that's what I thought.
Those are internal forces now.
Okay.
Yeah,
good,
you're cutting these members to make the internal forces external, basically.
Okay.
And you ignore all the other
Yeah,
internal
because I
forces.
thought about it, and it would be like too complicated if you had to include those. It like wouldn't work.
Yeah, and it's the point. The beauty of the free body diagram is just telling you you're just doing all the external forces in the free body diagram.
Okay, cool.
So you want us to do 4 equations? So like 2
Uh,
moments?
No, you just need to do 3.
What about you said 2
Each
moments?
moment equation will solve for one unknown, and you have to do one sum of fx or fy.
Oh.
So you said just do 2 moments just for the point of doing it to like understand it better.
No, do 2 moments because one moment gives you one force, another moment gives you another force, and then like the fy or fx will give you the third force.
So like probably
You guys have sat here. You haven't solved a single problem the whole hour, have you? You've just been chit chatting the whole
It's
time.
Friday. It's Thursday.
Thursday.
It's the equivalent of Friday.
That's true.
All right. Well, have fun over the weekend. Remember, there's a quiz this week. Quiz this weekend. Yeah. And I'm making some multiple choice questions for the quiz. I know. Got to take this class seriously. If you're going to learn this stuff, if you're a mechanical engineer, are you a mechanical engineer, Isaac, or civil? Either one. It's all statics. Good. Well, that's why you were talking about something else the whole time. Yeah, good. That's why I heard all that suppressed laughter for the whole class, because it's your favorite. Laughing for joy.